Bismillahirrahmanirrahim. Assalamualaikum. Hello, hi everyone. So today we are going to be taking lecture number 26, and it's going to be about solving the problems of chapter number 6 from the book Process Dynamics and Control for Seborg. And you're going to like the questions in chapter number 6. It's very interesting. And let's start with our first problem. So here we have 6.1. 6.1 actually 6.1 talks about some plotting, so we're not able to do this. It's not straightforward that we are able to do this. However, it says here plotted poles and zeros in the complex plane, so we don't know what are the poles and zeros, but I just want to give you the idea about, remember, the poles are plotted as X and the zeros as circles, and the poles are the roots of the denominator and the zeros are the roots of the numerator, and then you're going to see that on the complex plane and see which one is dominant. Okay, so don't worry about it. So we are going to solve something similar in number 2. So in number 2, I'm given the transfer function g of s is equal to 2 into s plus 0.5 over s plus 2 into 2s plus 1 into e to the power minus 5s. Okay, so for that problem that I have here, I want to find the poles and zeros, right? And to find the poles and zeros, I need to put this in the standard format. And to do this, we need to look at it. So we have 2 into s to the power 0.5. Okay, that is 2. Okay, so that's 2 into s plus 0.5 over s plus 2 into 2s plus 1 into e to the power minus 5s, right? Yep. So these look like in a standard format. And what is the standard format? Just to get the idea and remember that. So this is like equal to some kind of a k into tau a s plus 1, right? Over tau 1 s plus 1 into tau 2 s plus 1. If there's more, there will be more s plus 1. So the only thing that I can see here that I need to standardize is that 0.5 here, which is not plus 1. And in order to do this, we can take 0.5 as a common factor. And taking 0.5 as a common factor, it will be like 2 multiplied by 0.5. And here, because I'm taking 0.5 as a common factor, so it will be 2, sorry, 2, because 2 into 0.5 is 1, right? So 2 into 0.5 is equal to 1, so that's correct. Plus 1 into e to the power minus 5s, okay, so that's like that, divided by s plus 2 into 2s plus 1. Okay, now looking at the poles and zeros, and here are the poles and here are my zeros, and for the poles it's very obvious that I have 2s plus 1 is equal to 0, so s is equal to minus 0.5, so here I have s is equal to minus 0.5, and for the zeros I have s is equal to minus 2, and it is also equal to minus 0.5. And now to have this on the s-plane, so something like that, okay, on the s-plane, and putting that on the s-plane, we are going to have the poles. I'm going to plot the poles now. Let me put that on white. So poles is usually represented as x, so s is equal to minus 0.5. I just remind you, this is the imaginary and this is the real axis, so here I have no imaginary roots. So s is equal to minus 0.5. Let me say just for any just representation, so this is minus 0.5. What about the zeros? Oh my god, I confused you. Okay, I confused you because if I'm talking about the numerator should be zeros, right? Here we have the zeros, and here we have the poles. Okay, so that is that, and that is that. Okay, so coming back again after this confusion that we had done, so s is equal to minus 0.5, and s is equal to minus 0.5. Here is the s. Oh my god, another mistake. Why? Because I have kept an x. I shouldn't put an x. Zeros, I should have what? I should have a circle. So again, I'm going to fix this, and this is s is equal to minus 0.5. Now things look better. And for the poles, I have minus 2 and minus 0.5. So it is going to be something like that. So there's like minus 0.5 and minus 2. Definitely the zeros will be like having an effect. And in this case, can you remember this overshoot or undershoot? Can you remember that? It's going to be an overshoot. Okay, if it's on that side, it's on an overshoot. And in this case, there will be an overshoot. And this is not oscillatory because there are no complex roots. So if I'm going to draw my figure will be something like, instead of being something like that, no, it will not be like that. It will have an overshoot, and then it's going to go to settle down. Okay, it will go and settle down. Okay, so this is how to represent my system. So that these are the zeros and these are the poles of the system. Well, there's something as well, which is something, sometimes it happens for control purposes, but we always advise not to do it. Okay, not to do it, where you cancel a pole and a zero. Okay, you cancel a pole and a zero, and if you do this, by the way, that means it's like you're canceling out a pole and a zero, which means you're canceling out this term here, right? You're canceling out this term here, and canceling out this term here, okay, canceling out this term here will have a problem. Why? Because it's like you're having only one pole. And here, when you're having only one pole, it looks like there's no overshoot, and the system will be looking like what? It will be looking like something like that. Okay? It will be looking something like that. And actually, this is the correct one, and that is not correct. And we need to plot look like how does that look like, but definitely here it shows that it is cancelling out poles and zeros. So we do not advise to do this. So this is something else that you also need to consider. So put in standard gain transfer constant form. I put this in standard form, the s plus 5 to 2s plus 1. Determine the gain. The gain is the 2. Okay, gain is 2. Sorry, it's not 2. After we put it in standard form, it was different. It's 2 multiplied by 0.5, right? So it's 1. Gain is 1. And the time constant, we have 1 and 2. What about the gain poles and zeros? The poles and zeros we have already identified. Okay, we already had identified poles and zeros to be minus 2 and minus 0.5, and the zeros as minus 0.5. Now, if the time delay is replaced by a 1 Pade approximation, repeat part B. So if you replace this e to the power minus 5s with a 1 approximation, of course the answer is going to be different in some way. And in this case, how is it going to be different? It's going to be different in the sense that we are going to substitute. Here, the answer will be like, let me write it, g of s, it will be 1 already. So that is 2s plus 1 over that was 0.5 s plus 1, right, into 2s plus 1. And actually here you cancel the dominant ones, which is also like, oh my god. And now we are going to multiply by e to the power minus 5s. E to the power minus 5s, if you remember from Pade approximation, so this is like Pade, and Pade approximation says that you will have e to the power minus theta s is equal to 1 minus theta over 2s over 1 plus theta over 2s. Okay, so in this case it will be, my system will look like 2s plus 1 into 1 minus, here we had e to the power minus 5s, so this will be like 1 minus 2.5s over 1 plus 2.5s, okay, over 1 plus 2.5s. And this is just the continuation of what we have. So what do we have here? The thing that I can see I have here, I'm adding a 0, okay, I'm adding a 0, and I'm adding a pole, because the question is asking me, after you do the Pade approximation, find the zeros and poles. So here it looks like my poles that were only -2 and -0.5, now I have something else which is here it is 5 or 2.5. What will be the answer? 1 over 2.5. 1 over 2.5 is like 1 over 2.5 is 0.4. I think it's 0.4, right? Just a second. So that will be -0.4. Okay, so just to look at it, this comes from here. And for the zeros, I'm going to have one more 0. So the zeros, which are usually represented as circles, is equal to we already had this as -0.5. Now we'll have +0.4. Okay, so we'll have like something like an undershoot and an overshoot. Okay, so an overshoot, and this is why they always, you have a 0, they call it a lead lag, because you could have undershoot and overshoot, or either of them. It's called a lead lag system. A lead lag when you have a 0 at the top. Okay, so that is for the answer of 6.2. I think so. Now we can shift to solve. We can now go to 6.5. 6.5. Because 6.3 and 4 are just derivations. It is good, but I would like to solve problems now. Okay, so we will go to 6.5. So going to 6.5, here we have 6.5. Okay, great. So a process has a transfer function, of equation 614 with k, tau 1, tau 2, and if tau a has the following values. Okay, so we're talking about the standard form. Okay, so what is our standard form? So 6.5, our standard form is k over k into tau a s plus 1 into tau 1 s plus 1 into tau 2 s plus 1. Okay, and in this case, what are our values? We have k is equal to 2, tau 1 is equal to 10, tau 2 is equal to 2. Okay, 10 to k is equal to 2. So that will be 2 into tau a s plus 1, which will be different for different values, over 10s plus 1 into 2s plus 1. Okay, so that's the question. So what do we have here? We say that now if tau a has the following values, it will have 20, 40, 1, -2. We have 4 different cases, so we need to solve every case. Calculate the response of a step input of for a step input of magnitude of 0.5, so that is 0.5 of s, and plot them in a single figure. So we're going to plot them all in a single figure just to show how does that look like. How does that look like on a single figure, showing some of them that have an undershoot and some else that have an overshoot. And so it's beautiful to look at all the responses together. So what do we have? In case 1, let me continue the problem. What conclusion you will make concerning the effect of 0? So we're going to talk about the effect of 0, whether dominant or negligible, and then we're going to say undershoot or overshoot or negligible. Is the location of the pole corresponding so long as... Don't worry about that part. Okay, so for case A, tau A is equal to 20. Tau A is equal to 20. So in this case, let me write the poles, because the poles are going to be fixed for the whole problem, right? So what are the poles? The poles are, which are the denominator, the roots of the denominator, right? So they're going to be here. So s is equal to -1 over 10, which is -1 over 10, which is -0.1. Okay, and I have my poles is equal to -1 over 2, which is -0.5. So I have two values here, -0.1 and -0.5. And in the case So let me draw this also on a figure. That will be really beautiful. So I'm going to have a figure here in the center. That's my figure. And what I'm going to have, I'm going to plot my zeros and poles. So this is my imaginary axis and that is my real axis. So what do I have? I have poles which are minus 0.1 and minus 0.5. So this is my poles. This is how I represent my poles. So my poles, for example, here it's minus 0.1 and about 5 times here is minus 0.5. So this is like minus 0.1 and minus 0.5. Great. What about the poles? Now for the poles, we need to solve for the poles. So in the poles, what did it say? It said that the first value, the case 1 value, so we're going to check case 1. And in this case 1, I have tau A is equal to 20. And if tau A is equal to 20, my 0 is going to be S is equal to minus 1 over 20, and that would be minus 0.05. And in this case, for minus 0.05, you will see that minus 0.05 just sits here. Okay, you see it sits here, and sitting here, that means the 0 is going to be dominant, right? And because it's very close to the imaginary axis, other than that it is closer to the imaginary axis, it is very close to the imaginary axis. So if it will be dominant, that means there will be an overshoot because it's sitting on the left hand plane. Okay, because it's sitting on the left hand plane here. So I will have an overshoot. So this is the area in which if the 0 is dominant, you will have an overshoot. Okay, and the right hand plane, you will have an undershoot if it is dominant, of course. So in this case, it is dominant, we have an overshoot. So now we can also plot our first graph. Okay, we can also plot our first graph, and just to have some space here, okay, just to have some space here, so I'm going to plot the system here. Okay, so my first graph that I would like to plot here would look most probably something like that. Okay, something like what happened with the way? Okay, something like that. Let me draw this in a different color. So something like that, and then it goes down and it settles. Okay, so that is my first figure for case 1. This is case 1. Okay, so I'll write here, just write C1. Okay, case 1. Okay, so let's go to the second one, and going to the second case, I have case 2, where tau A is equal to, I don't know, let me see, tau A is equal to 4. Okay, so tau A is equal to 4. So if tau A is equal to 4, my S is going to be minus 1 over 4 minus 0.25. And in this second case of minus 0.25, okay, so this is like for case 1, okay, so this is like case 1. Now I'm going for another case in which my 0 is sitting here, which is case 2. And in this case, you will get, oh my god, is that an overshoot or not? So in this case, it's not easy to decide. And you can say that you will have an overshoot because it will still have an effect. So it will lift up. It will lift up of my response. And since I'm saying lifting up, that means if my figure will look something like that, maybe it will lift it up to be something really higher. Okay, so it will be something higher that goes like that. Okay, so that is what we would expect. Okay, so there will be something like here, like a lift up of this overshoot thing. Okay, in the exam, if you say that I'm going to consider this as something like that, for example, a small overshoot. Okay, so this is like my set point, so I will go to have a small overshoot. It's very difficult to specify this overshoot because it's not dominant. But you said that I'm going to have a small overshoot, and then it's not oscillatory overshoot, and then it goes constant like that again. If you do this, no worries. I'm not going to consider that as wrong because it's difficult to know the exact response, but that will be good enough for you to show that there is a small overshoot here. Okay, so in this case, if you do this, it is also fine for us. Let me see the third response, okay, and I will return that just to what we had here. Okay, so what do we have here? So we had our response that looks like that. Okay, so the C3 is case 3. So I have case number 3 where tau A is equal to 1. So in case 3, tau A is equal to 1. So that means S is equal to minus 1 over 1, which is minus 1. And in this case, I'm having my third case, and definitely this is going to be negligible, okay? So this is my third case, and talking about now the negligibility part, this will be negligible, and my third one will be something that is like that. And definitely is going to be lower than the previous one, okay? It's going to be lower than the previous one. So this is my third case. So I have case 1, and this is my case 3, and that was my case 2. Finally, I will look at my final case, case 4, in which I have tau A is equal to, let me look, it's minus 2. So tau A is equal to minus 2, so minus 1 over 2, which means it is plus 0.5, I would say, plus 0.5. So that will be plus 0.5. So now for plus 0.5, again for sitting a middle way between, it's like middle way between these two, right? A middle way between these two. So you will consider like that to be a small, very small undershoot. As I said, for C2, you could show that small overshoot as well. So in this case, what do I have? I'm going to have a small undershoot, and then I'm going to have my response that will also go to the same steady state. So all of them will go to the same steady state values, and you can see from the final value theorem. If you apply the final value theorem, you'll find out that all of them will go to the same steady state value. Okay, so these are the 4 cases, and we're just looking at that that point here causes an undershoot, that 2 points cause overshoot, and that case 3 point is negligible. Okay, so if I'm going to write now this, I'm going to write it now. So the case 1 was an overshoot, case 2 was an overshoot, case 3 was negligible, and case 4 we had an undershoot. Okay, so these are the 4 points that I need to mention. I would like to do, just to show you that it goes to a set point that is similar. So limit S approaches 0, that's the final value theorem. For S approaches infinity, for S, and I have my y of S, what is my, yeah, it is the standard form, right? Any value taken by the tau A S plus 1 does not affect me, so I'll just put it as tau A S plus 1. And I had a step input of 0.5, sorry, so I'll put that. So I have a step input of 0.5. Okay, so that is my y of S. You take y of S after you introduce your u of S, right? So this is S into y of S, and then you're going to put y of S. Y of S is what? Is 0.5 over S multiplied by the function that I have. I will just show you the function just to make me feel more comfortable. G of S is what? Actually, G of S is y of S over x of S. Okay, and if I want to find y of S, I need to multiply the input with this function here. So it will be, so this is my function of y of S, right? This is my function of y of S over 10s plus 1 into 2s plus 1. And if I want to just multiply by 0.5 to 2, it will be 1 over s multiplied by this whole bit here. So I'll just consider now my final form. My final form is this, 10s plus 1, right? Sorry, tau A s plus 1. and I have 10s plus 1 into 2s plus 1. So in this case, if I substitute s approaches 0 to find what happens in infinity, so this will be 0, okay, so this will be like 0, this will be 0, this will be 0, and actually it shows that it will be equal to 1. So it will be equal to 1, so that this final value that I have here, the final value for all of them is going to be 1. Okay, and this is the plot of my y of t against time, okay, against time, which is in seconds, and my of t, I'm not sure what is the units now here, but so this is the way how you show it. So that is the solution, that you have for 6.5. That was a good problem, so let's go and solve now 6.6. Okay, so in solving 6.6, I think so 6.6 here, it shows me that I have two systems, a process consisting of an integrating element operating in parallel with the first order. So this is like two systems together, and it's a kind of a derivation. What is the order of the overall transfer function? What is the gain? In what conditions is the process gain negative? What are the poles? And I think so there are many questions here that we need to consider. And let's look at the solution of 6.6. And in this case, you already can see that I'm having an addition. I am having an addition of two transfer functions. How did I know? I mean, it shows here, right? Plus plus. So you're adding these two transfer functions. So y of s divided by u of s is equal to k1 of s, k2 plus k2 over tau s plus 1. Or you could say y of s is what? Is u multiplied by k1 over s plus u multiplied by k2 s tau s plus 1. So both of them are going to be similar. So going to 6.6. Okay, 6.6. That is good enough. Okay, so 6.6. So I'm going to have a system which is y of s over u of s is equal to k1 over s plus k2 over tau 2s plus 1. Okay, over tau 2s plus 1. And now if I just want to take a common denominator, I'm going to have something that looks like that. So this is k1 into tau 1 s plus 1. Okay, instead of saying tau 1 and tau 2, I just have only one tau, right? I'll just put it as tau. So this will be like k1 into tau plus k1, k1 into tau plus k1, yep, that's right, plus k2s. So k1 tau s plus 1 plus k2s divided by s into tau s plus 1. And if I just rearrange this thing, this will be like k1 tau plus k2s. So this is like my tau as plus 1. Did you see this? This is like my tau as plus 1. It looks like it. And this is divided by s into tau s plus 1. Okay, and that is normal. Okay, the one we have at the denominator. So putting that in a standard form, is that in a standard form or not? I think I have missed something here just before. So if you can remember, this is not k, this is not 1, it's plus k1. Okay, so k1 multiplied by tau s plus 1 is k1 tau plus k1. Okay, so that is k1. In this case, I'm going to have k1 here. And this is not in the standard form. To put it in the standard form, it should be tau as plus 1. So this will be like k1 tau plus k2 divided by k1. Okay, so that is divided by k1, and this is that. So that is like s plus 1. And since I divided by k1, I need also to multiply by k1, right? So I need to multiply by k1. Okay, now it is like tau s plus 1 over s into tau s plus 1. Great. Oh, okay, so what was the question? We forgot what was the question. Okay, so what was the question? 6.6. What is the order of the overall transfer function? Well, the order of the transfer function, we can know the order by knowing the order of the denominator. Okay, so the order of transfer function, we look at the order of the denominator. And in this case, the order of the denominator, we have s and tau s, so definitely it is s squared. So we are going to say that the order is a second order, okay? It's a second order. So that is for part A. Okay, what do you want from part B? What is the gain of GS? Okay, G of S actually is very clear. Sorry, what is the gain? So the gain is here, K1 to tau AS plus 1. So the gain is K1. Gain is equal to K1. 1, it will be negative. That's easy. It's K1. If it's less than 0, it will be negative. Okay, so let's go to part C. Okay, let's go to part C. And part C says, what are the poles of GS? What are they? Where are they located in the complex X plane? Okay, now we are talking about the poles. The poles it is the denominator again. So I'm going to write this. So poles are the roots, right? They are the roots of the denominator. And in this case, my poles is S is equal to 0. So I have S is equal to 0 and S is equal to minus 1 over tau. So these are the poles, and if I'm going to plot them on the plane, so there's one which is here, 0, right? And there's another one which is here, which is minus 1 over tau. Okay, so this is 0 and this is minus 1 over tau. So I have two poles, and this is how I plot it on the plane. Great. So what is part B? What are the zeros of G of S? Where are they located? Okay, so now just to continue, so part B, the zeros are the roots of the numerator, and in this case my numerator here, so this whole numerator is equal to 0, so tau AS plus 1 is equal to 0, S is equal to minus 1 over tau A. Do you remember that? Okay, so that will be K1 tau plus K2, which is tau A, over K1, which is tau AS plus 1, is equal to 0. Tau AS plus 1 is equal to 0, right? So that is the term. So that will be minus 1 over tau A, and S, the zeros, are going to be minus K1, I'm just doing it quickly, over K1 tau plus K2. Beautiful. Now the question is that one we are going to decide sorry, under what condition under what condition will one or more of the zeros are located in the right half S plane. So it is asking me on what are the values that based on which I'm going to say that is going to be on the right hand plane. Okay, that is going to be on the right hand plane. And if you think of it, there are some assumptions that we need to consider here, and some of those assumptions are what is the value of tau 1 and what is the value of K1, right? Because the values of K1 and tau 1 would help me to identify that it's going to be on the right hand plane or not. Okay, so to be on the right hand plane, that means my zeros need to be positive. Okay, my zeros need to be positive, and in this case, what is it? It is negative. So I need this term here to be negative. So if this term is negative, that will be negative, with the negative is positive. So based on this, what I'm trying to say here, and let me say that this is like negative, so that the whole thing becomes positive to be in the right hand plane. So I'm saying that my condition here is that my K1 over K1 tau plus K2 should be positive, should be greater than 0. It should be negative, should be less than 0. And based on that, what will happen? I'm going to have that to be positive. And of course, if you're going to look at this, this is going to multiply by 0. So the condition that I'm going to drop out, okay, the condition that I'm going to drop out here is that K1 is less than 0. Okay, but considering K1 is less than 0 and the denominator as well, okay, and the denominator, which is K1 tau plus K2, is greater than 0. Because if K1 is greater than 0, but K1 tau plus K2 is less than 0, we will have negative. It's like negative divided by positive, or positive divided by negative to give you a negative value, right? The whole idea is for that to be negative. And if it is negative with a negative sign here, a negative with a negative sign, it will be positive. So, and that was the question. When it will be on the right hand plane, if it's positive. How to be positive if this part is negative? How it will be negative? If either numerator is negative and this is positive, or the numerator is positive and the denominator is negative. So that's the whole idea of part D. Okay, great. So what about now part E? Under what conditions, okay, under what conditions, if any, can this process exhibit both a negative gain and a right half plane 0? Oh my god. This is driving me crazy. Okay, it becomes more complicated if you don't understand the question. Under what condition, if any, can this process exhibit both a negative gain, so K1 is less than 0, and a right half plane 0? And a right half plane is zero. That means that is possible if the K1 tau plus K2 is greater than 0, and that is the only possibility that you have. That is the only possibility. So in this case, for part E, it says the gain is negative, and whatever that 0 is greater than 0, so the gain is negative if K1, definitely, this is the gain, right, is less than 0, then the zeros, the zeros, if you remember, these are my zeros, right? Like this is my 0 here. This whole term is my 0. And talking about this whole term is equal to 0. So if K1 is negative, okay, if K1 is negative, that will be a positive term. So my denominator need to be positive. Why? Because if it is positive, it will be positive over positive. It will be on the right hand plane. I hope you got it right. So this, in this case, K1 tau then zeros, which is K1. Okay, sorry for that. K1 tau plus K2 is greater than 0. So I hope you got it. Okay. I know sometimes with the derivation thing it becomes not very pleasant sometimes to your heart. But it's good to do these calculations, because you need, if you get to a higher degree, those kind of calculations could be normal for you to do, because you need to derive some new expressions. Okay, great. For any input change, what functions of time response will be included in the response? And if we are just looking at what is y of t for any input change. Okay, in this case, if I have any input change, which is m over s, to a second order process, okay, so we are going back to our knowledge about the overdamped and underdamped. So if I have a step input to a second order process, what we are going to have, first I'm going to look at my poles. Is it smooth or not? Okay, is it smooth or oscillatory? And number two, if it is stable or unstable. Okay, or unstable. In this case, my taus are positive, and if my taus are positive, which means my poles are going to be negative, and if my poles are negative, then I'm going to say that they are stable. Okay, so in this case, I'm considering my taus are positive, so that is my assumption here. Okay, I'm taking the assumption here that the taus are positive. Maybe the problem said that it was a stable system. I can't remember if it said that. A process of an integrating element, well, it says integrating because of that. And we have a stable system here, which looks like a stable system. So most probably after what we had obtained, it still looks like stable for me. Oh my, okay, oh my god, okay. So that was not the system was looking like that. The system was looking something like that. Okay, and that what makes it now like the part of the integrating thing. Okay, the integrating, and let me see if s approaches 0 for s of y of s, this s may drop out, but I'm going to have something divided by s is going to be infinity. No, definitely this could be not stable. Okay, so I will not say that's a stable, that will be more like unstable, even though that for a moment I thought that I'm going to get an exponential term, but that is not exponential, that will be unstable. Is it oscillatory or not? We could have thought of its oscillatory if we have something in the denominator as what? As a complex root, but it's not oscillatory, it will be smooth. And now we think of undershoot and overshoot. I mean, if it's unstable, I don't think so we need to think a lot about overshoot and undershoot. Okay, so that was part F, and it's very clear that I'm going to have, as asked by also part G, that I'm going to have a T term here. Okay, because that's going to be like m over s squared, right? And I'm going to have an exponential term. If you want to look at that, okay, e to power minus some exponential term, t over tau. Okay, so how did I know? If I put this together, so this is like m over tau 1 s squared into tau a s plus 1 over tau 1 s into, sorry, I already multiplied this by the s, over tau 2 s plus 1. Okay, so this is the term that I have. So if you want to distribute this, you have something over s squared plus something else. Sorry, it's not like over s squared, so it's going to be a over s plus b over s squared, like that, plus c over tau 2s plus 1. Okay, and what I wanted to say is that this is going to be like a term a plus another bt plus c e to the power minus t over tau. Okay, so that is what I try to mention here. Okay, what I try to mention here, that you'll have an exponential term and you have a t term. Great, so that is 6.6. That is 6.6. I think this is good enough for this video, and we are going to take a break and see you for the next video, where we are going to continue solving chapter 6 problems, and we are going to solve number 7, 8, 9, 10, 12, 16, 20, and 23. We have big number of problems to solve, and by that, all the best, and I hope that you gained from what we have taken so far. So thank you very much. See you in our next video. As I was advised, be happy and reward yourself that you have done something good today. Okay, and make your smile bigger. Okay, I think this is smile. Yeah, now it's bigger. I don't know what's going on with his teeth. Okay, see you then. Thank you very much. Thank you very much. Masala.